In section 7.5, we're going to continue to work with exponential functions, but now we're going to work on exponential decay functions. So if you remember, we worked with growth models which come in horizontal and turn vertical. A decay model does the opposite. It comes in vertical and goes out horizontal. So one is showing exponential growth, or increasing values, and this is showing decay, right? So our values, as we approach positive infinity, as x approaches positive infinity, then y is going to approach 0. Okay, or that's an oversimplification. In the root form of this model, y will approach 0. It'll approach other things depending on the parts of the specific equation. So when we take a look at an exponential decay model, you'll notice that the thing that has changed from growth is that instead of a addition here inside the binomial, we have subtraction. So it's going to be a growth. It's not a growth rate because it's less than 1, so it's not a growth factor, it becomes a decay factor. So r is the decay rate. In the other model, it's the growth rate. T is still the time period, A is still the initial amount, but now 1 minus r is called the decay factor, and r is the decay rate. So either way, it's really the same as the growth model, it's just that you have a negative growth rate, which makes it a decay rate. Okay, so it's the same basic model. If I want to go ahead and write a function rule out of a table, what I want to look at is what's happening with my output. So I know when x was -1, y was 50, and here it goes down by a factor of 5 and another factor of 5. So you can see, right, 50 divided by 10 is 5. 10 divided by 2 is 5. And 2, right, divided by 0.4, that equals 5. So we're having a factor of 5 going on here. So it might look something like this: y is equal to a times 1/5 to the x power, right? Because I'm dividing by 5 each time as we move along. So then the question is, what value of a would give me 50 here at the beginning? So 5 times 50, -1. Right? So when x was -1, that would be y is equal to a times 5. So I'm thinking this value would be 10. So my hypothesis is it's 10. So a times 5 is equal to 50, so a would be 10 times 1/5 to the x power. Okay, and let's test to see if that works. When x is -1, this inverts and becomes 5. That gives me 50. When x is 0, this becomes 1 times 10 is 10. When x is 1, it's 1/5 times 10 is 2. So this is the equation. Okay, if I did this sort of by rationing it out. I could equally create a system. So I could say that y was 50 when x was -1, and y was 10 when x was 0. But I know that b to the 0 power is going to be equal to 1, so I can see a is equal to 10. And if I plug 10 into this model, if I divide by 10, 5 is equal to b to the -1 power, right? So if I have 5 is equal to 1 over b, and I multiply both sides by b and divide both sides by 5, I get b is 1/5. Okay, so I could do it in a more formal mathematical way, or I can do it by just sort of rationing things out. And you'll notice that when x is 0, it's a big helper, because anything to the 0 power is going to be 1, and that means that this item would be my A value pretty much every time. So let's look at graphing one. Right? We still have the same basic functions of the growth model, in that what's important is I know it starts vertical and I know it leaves horizontal. What matters is the curve and where it takes place and how steep it is. So again, I'm going to use -1, 0, and 1 because that really helps me understand. So when x is -1, then y would be 3/2. When x is 0, y will be 1, and when x is 1, y will be 2/3. So they're very easy to do. So I have 1.5, 1, and 2/3. So I know that my graph is going to come in along here and go out along there. Okay, so remember, if I'm working with exponential growth or decay, the inputs I pick are pretty much the same. These are the easiest inputs to derive the information I need. Okay, again, reviewing a little bit, we have exponential growth and we have exponential decay. All right, and what matters is that, and the way I can tell them apart is here b has to be greater than 1, and here it has to be between 0 and 1. If it's equal to 1, it's not an exponential model at all. It becomes a linear model. A has to be greater than 0, right, for it to exist above the line. Quite honestly, if A is less than 0, then all that happens is it inverts, so it doesn't look like this, but it looks like that instead. Right? So it's not that you can't have a negative A for these models. You can. It just changes the way they look. Okay, now if I want to create the rule based on a graph, I can see this is a decay function, right? And I've got 2 points. So again, I know that y was 8 when x was 0. I'm taking the coordinates, right, and using them. I know that y was 1 when x was 4.8. That's a little awkward, right? But this will allow me to find out that, right, I know that b to the 0 power is 1, so a is equal to 8. So 1 is equal to 8 times b to the 4.8, right? I've already classified this as a decay function, right? If I divide by 8, 1/8 is equal to b to the 4.8. So I know that some number to the 4.8 power is going to become 1/8. So I'd want to go ahead and find a value of b that would equal this. So what I would want to do is I would want to take a root of either side. The 4.8th root of 1/8 would be equal to b. That's a little complicated to do, but I can do that. So I'll have open parentheses 1 divided by 8 close parentheses, and I'm going to take it to a power, and the power I'm going to take it to is 1 divided by 4.8. And this is my answer, 0.65. So b is equal to 0.65. So if I wanted to write the rule, it's y is equal to 8 times 0.65 to the 4.8 power. Okay, remember, I'm using the idea that I'm taking both sides of this equation to the inverse power of 4.8. So 1 over 4.8, which gives me b to the first power. And that's what leads me to have the 4.8 root on the other side. Right? So something like this is what guided how I used my calculator. So I do roots by creating exponents that are fractions. Okay, if I wanted to work on a multi-step problem, I've got acres of ponderosa pine forests, and they're decreasing by 0.5% annually. Now, what's going to be really important here is when I put that in as my decay rate, I have to make sure that I make it a decimal. So if I want to write the function, I know that y will be equal to my starting situation. In 1963, that's when we're starting, there were 41 million acres, so 41 million. 1 minus 0.05, that's 5% as a decimal, and it's done annually, so it's just going to be t. Okay, if I simplify this, it becomes y is equal to 41 times 0.95 to the t power. So how do things look in 2002? Well, that's 9 years later. So y would be equal to 41 times 0.95 to the 9th power. If I go ahead and pull out my calculator, I'll do 0.95 to the 9th power, and that's what it equals, times 41 equals, so 25.84. So 25.84 million acres. So you can see it's almost half. Okay? So that's working with exponential decay models.